Hey folks, today we're going to talk about reasonable domains and ranges for your square root functions. In the last set of notes, we talked about transformations of functions, and we created equations for those square root functions, and we even identified the domain and range. Well, today we're going to talk about reasonable domains that are going to happen when you don't have a graph to look at. So we need to remember kind of the anatomy of a square root. So if I have up top a square root, this is my radical. And then anything inside this is called my radicand. So whenever we talk about the radical, that's the actual symbol itself, and then the radicand is all of the stuff that is inside. So remember that you can't take the square root of a negative number. You end up with an imaginary or a complex number. So we need to remember that. You cannot have a negative radicand. So think about on a number line where negatives are. Negatives are the numbers that are to the left of 0. So all of your radicands need to be greater than or equal to 0, and we're going to use that in a moment. The radicand must be greater than or equal to 0. Because on a number line, that's where the non-negative numbers are. So sometimes it's really simple to determine a reasonable domain. I take my radicand and I set my radicand greater than or equal to 0, because that ensures that it's positive, right? So I'm going to determine the x's for which this works. I'm going to solve for x. I'm going to do the inverse of plus 3, which is minus 3, and that zeroes out. 0 minus 3 is negative 3, and my domain for this function is all the x values that are greater than or equal to negative 3. Now let's see what that would actually look like in a graph. So if I have my parent function here, and I transformed 3 units to the left, so I shift to the left, 1, 2, 3. Let me use a different pen. Nothing else changes, so I still get 1, 2, 3, 4, up 2. I still get this square root function here. Now it turns out that it keeps going on and on forever, but instead of the domain being all the x values that are greater than or equal to 0, here's my boundary now. So if my boundary is right here, that's at an x value of negative 3. So all my x values are to the right or greater than or equal to negative 3. So that's kind of what it looks like now, is if you've shifted to the left a little bit, then your x value here in your domain is going to be a little bit less. So let's look at number 2. Pause the video and identify the radicand and set it greater than or equal to 0. So we should identify the radicand. It's 1/2 x minus 3, and we should set it greater than or equal to 0 to ensure that it's not a negative number. It needs to be positive. So that's what you should have. Now I want you to pause your video again and try to solve for x to find the reasonable domain. Pause your video. So in the process, you should have added 3 to move the constant. You should have unmultiplied by 1/2 by either dividing by 1/2 or multiplying by 2. Both of those are equivalent operations here, so I just went ahead and multiplied by 2. 2 times 1/2 is 1, so that will cancel out. And then on the right side, I get a 6. So my x values should be greater than or equal to 6, and that's my reasonable domain for this square root function. So I'm going to scoot this up. We have the same kinds of problems, except these have quadratics underneath the radical. So it says, be careful on x squared under the radical. There will be 2 intervals for the domain. So that means you will have 2 inequalities for the domain. You're going to check by subbing in some values to see which intervals are going to give you the reasonable domains, the ones that don't make the radicand negative. So same idea applies. Identify the radicand. Okay, because we don't know exactly where our intervals are going to be, what I'm going to do is I'm going to go ahead and set this equal to 0, and I'm going to solve for x, and those x values are going to be kind of like my boundaries, my reference points for my domain. So this is x squared minus 9. I could do this two ways. I could either factor this difference of perfect squares, or I could move the 9 to the right side and square root both sides to get an answer. So I'm going to go ahead and move the 9. And I'm going to unsquare by square rooting. The square root of 9 is not just positive 3, but it could be negative 3 as well. So we end up with two answers, and I'm going to graph them both on a number line so we can start picking values to determine where our reasonable domain is. Okay, so I am not sure if my reasonable domain will be all of the x values that are less than or equal to negative 3, or greater than or equal to positive 3, or maybe it's going to be this section in the middle. So I'm going to pick some test values. And I went ahead and I put one test value already, which is this 0, this place in the middle. So I'm going to go ahead and substitute a 0 for x right here. So 0 squared is 0, and 0 minus 9 is negative 9. So I end up with a negative 9 as a radicand if I use 0 as an x, right? So 0 squared minus 9 is negative 9. I can't have a negative inside that radical, so that means this middle section is not where my reasonable domain lies. So now let's pick a number out here. So it could be anything less than negative 3. It could be negative 4, negative 5, negative 6, whatever you want it to be. I'm going to make it negative 4. And I'm going to substitute negative 4 here. So negative 4 squared is 16. And 16 minus 9 is 7. And that's a positive number. That can be under the radical, so that's good. All of this area over here is correct. So my x values can be less than or equal to negative 3. And finally, I need to pick an x value out here. So anything greater than 3, maybe I pick a 4. So if I substitute 4 as an x, 4 squared is 16. 16 minus 9 is another 7. That's a positive radicand, so that's perfect. That will work. So I can have x is less than or equal to negative 3, or I can have x is greater than or equal to positive 3. And those are my two inequalities for my reasonable domain. So let's try example 4. In the same way that we did example 3, we're going to identify the radicand, set it equal to 0, and we're going to try and solve. We're going to get two different answers because we have this x squared nature going on. So when you solve this polynomial, you can only solve by factoring. So I need to think of two numbers that multiply to be negative 6 and add to be 1. Those two numbers are going to be some kind of combination of 2 and 3. If the product is negative, that means one of these needs to be negative, and it needs to be the 2 that's negative. That way, when you add them, you get a positive 1. So my factors are x minus 2 and x plus 3. And if I set each one of those factors equal to 0, I'm going to get an x value of 2 and an x value of negative 3. Those are my two boundaries. So I'm going to put those on a number line. Now I've already selected a number in between them, but I also need to select a number in the other places as well. So not just in between the points, but to the left of this point, maybe I pick a negative 4. And to the right of this point, maybe I pick a 3. So I need you to pause your video, and I'd like you to take a moment to substitute negative 4, 0, and 3 into x, into your radicand, and see if you get a positive radicand. If you get a negative radicand, that means that that section of the number line does not get included in your reasonable domain. So pause your video and substitute -4, 0, and 3 into your radicand. So as I substitute -4 in place of x, I learned that the radicand would be 6, so that would be okay. That's a positive number. If I substitute 0 in place of x, then I end up with a radicand of -6. That's not okay, so that means the middle section is not okay. Not part of my domain. And then if I take a 3 and I substitute it in place of x, I end up with a radicand of 6, which is a positive number, and that's okay as well. So that means that anything that is to the left of -3 and anything that is to the right of +2 are part of my reasonable domain. Okay. Let's open this up. The inside of these notes it reintroduces the idea of inverses, and we're going to be finding the domain and the range of functions and their inverse. So we need to remember how to find an inverse. Example set 5 says find the inverse of f of x equals 2x squared minus 6, and it says do it algebraically, which means that I don't need to graph and reflect over the line y equals x. I need to switch x and y and solve for my new y. So this is going to become x equals 2y squared minus 6. I'm going to peel away the outer layers first, so I'm going to move the -6, and then I'm going to move the 2, and then I'm going to unsquare. So pause your video and solve for y. I need you to move the 6, move the coefficient of 2, and unsquare. Pause your video and solve for y. So when you square root your left and right side, you square root a function and you end up with a positive and negative answer. So that does not give you a function. It just gives you kind of a sideways parabola. So instead of calling this the inverse of f of x, we call it the inverse of y. So that's my inverse of the function. And we found it graphically because the next portion tells us to graph both the function and the positive root inverse. So now we just want the positive root inverse, not plus or minus, but the positive root inverse. So 1/2 x plus 3. And then we need to state the domain and the range for each function. So you can start with whichever one you want. We've been graphing square root functions a little more recently, so perhaps I start with that one. Remember that whenever you are graphing with transformations, you can't have the 1/2 right next to the x. You need to put parentheses between them. So I'm going to go ahead and divide both of these by 1/2 so I can really see what's going on with these transformations. So the 1/2 is out in front. And then 3 divided by 1/2 is kind of like 3 times 2. So that's a 6. And this kind of shows me exactly what's going on with my function. So my square root function, parent function, should kind of look like this with the vertex at 0, 0, but I need to shift 6 units to the left. So 1, 2, 3, 4, 5, 6. And then this looks like it's horizontal because it's in there with x under the radical, but it looks like a compression. We know that anything under the radical is a lie. So it's not really a compression, it's a stretch by a factor of the reciprocal of this. So instead of 1/2, it's 2/1. So this is really a horizontal stretch by a factor of 2. So rather than going up 1 and over 1, I'm going to stretch this horizontally 2 units. So up 1 and over 2. So since we're talking about this graph, we can find the domain and the range. The domain is the values of x from the left to the right. There's a boundary right here. And that's going through an x value of -1, 2, 3, 4, 5, 6. So all the x values that are getting used are greater than or equal to -6. And the range, there's no y values being used down here, but here's the boundary, the very bottom of the graph. So the range is all the y values that are above this 0. So y is greater than or equal to 0. So for the original function has x squared, which means it's a quadratic. That also means that from the parent function, we're starting at 0, 0. There are some transformations that take place. If you have -6 outside, that's a shift 6 units down. And if you have a 2 out in front, that's a vertical stretch by a factor of 2. So rather than going over 1 up 1, you go over 1 and up 2. So I'm going to give you a moment to graph your f of x function, graph your parabola, shifting 6 units down and stretching vertically by 2. So pause your video and try to graph. So your vertex shifts down from 0, 0 to 0, -6, and then you have a vertical stretch by a factor of 2. So rather than using your quadratic pattern and going over 1 and up 1 and 3 and 5, you're multiplying that 1 and 3 and 5 by your scale factor of 2. So over 1 and up 2, over 1 and up 6, over 1 and up 5 times 2, which is 10. So I don't have space to do that last one, but that's what it would look like. For your parabola, is there a boundary on the left side? No. Is there a boundary on the right side? No. So when you go from arrow to arrow on the left to the right, that means the domain is all real numbers. Your range, all the y values, nothing is below this point right here. That's your minimum. So it's all the y values that are above or greater than or equal to -6. Perfect. So in summary, use transformations to graph, and then you can find the domain and the range of each function by looking for boundaries. So let's flip this to the back side. We've got one more problem. It is identical in instruction. So in example 6, find the inverse of f of x equals the square root of 4x minus 8 and do it algebraically. So what do we do with x and y? We switch them. How do we get the inverse? We solve for y. We can't get to y because it's under the radical, so how do you unsquare root something? You square it. What you do to one side, you do to the other. So x squared equals 4y minus 8. I'm going to give you a moment to finish solving for y. And once you finish solving for y, go ahead and write the inverse down here as well. Pause your video, solve for y. You should have moved the 8. You should have divided by 4. You end up with an inverse function of 1/4 x squared plus 2. So where the inverse of the function is, I've got g of x equals 1/4 x squared plus 2. So it is now your job to do two things. You need to graph the inverse and the original function, and you need to identify the domain and the range. I would advise on your parent function that you use the transformations. For example, you should shift 2 up, and you should have a horizontal compression by a factor of 1/4. Whenever you graph this one, remember that you need parentheses between the 4 and the x, so we would divide by 4 to really see what's going on with the transformation. 4x divided by 4 is x, and 8 divided by 4 is 2. So it looks like we have a shift 2 units to the right, and we have a horizontal compression by a factor of 4. So I'm going to pause the video and graph my functions. So for my parabola, 2 units up from the origin, that's my new vertex. A vertical compression by a factor of 1/4. That means instead of going over 1 up 1, I go over 1 and up 1/4, and that's hard to do. So we talked last time we did quadratic transformations, and you go over 1, 2, 3, 4, and you go up 1, 2, 3, 4. And that will give you kind of the layout of where your parabola should go. Again, over to the left, 1, 2, 3, 4, and up 1, 2, 3, 4. That way you are vertically compressing. For this one, I'm going 2 units to the right, 1, 2. And then this is a horizontal compression by a factor of 1/4. So rather than going over 1, up 1, I'm going over 1 and over, up 1 and over 1/4. So it's kind of hard to do. But every distance gets compressed by 4. So you kind of get the idea that it's going this way. So for your square root function, the domain has a boundary right here at 2. So all your x values are to the right of 2 or on 2. Your range, it's got a boundary down here at 0. So all your y values are greater than or equal to 0. Your parabola has no left boundary and no right boundary. So your domain is all real numbers. And your range, there's no values being used down here. This is your bottom boundary, your minimum. So all your y values are above or equal to that 2. So y is greater than or equal to 2.